Okay, so we spent a lot of time calculating out what the bending stress is. One other component of pure bending is what's the actual curvature of radius. Basically that bending radius that we have. So let's calculate that out. And so our bending radius, as we saw earlier, is given by the lowercase Greek letter rho. So now recall, as we talked about things, the stress in the x direction is negative y over rho, and also that the maximum strain that we can have in beam bending would be c, that distance from the neutral axis to the outside surface, over rho. So if we take these and rearrange them, and specifically I want to rearrange this stress max equation to isolate the radius of curvature, what I'm going to end up with is 1 over the radius of curvature will be the maximum strain divided by c. Now we're going to assume that we're in the linear elastic region, and so we'll be able to say Hooke's law, the maximum shear stress is going to be E times the maximum strain, which then we can say that stress max over modulus elasticity is strain max. We'll take all of this, plug it in for the strain max. And so what that leaves us with is 1 over rho is the maximum stress divided by the modulus of elasticity. And then we have C. So that replaces that through there. Now, the next thing to do is, I know what stress max is. Okay, so what is stress max? Stress max is mc over I. So I'll just take this and replace it in there. And so now I've got 1 over the radius of curvature is mc over I times 1 over EC, and the distance from the neutral axis to the outside surface cancels out. And what I'm left with is 1 over the radius of curvature is going to be equal to m over EI. And so this is the equation for calculating the radius of curvature. You're probably looking at me going, well, why isn't it just rho is equal to EI over m? This is classically the way that you'll see it in all the textbooks. It pretty much is just rho is equal to EI over m.